want to talk a little bit about entropy and probability. We won't spend much time on this topic, but I do think it's important in terms of understanding entropy. So entropy and probability. And essentially the deal is that systems tend to a state of maximum randomness because the random state is just more likely, it's more probable, right? If I had 10 quarters and I was to just throw them on the ground, the ordered state is they're all heads up or they're all heads down, right? They have to land in the same direction to be ordered. The odds of that happening are slim. So systems tend to a state of maximum randomness. Because the disordered state is more probable. Right? The probabilities of the ordered and random states are actually proportional to the number of ways that that state can be achieved. So if I had 2 quarters and threw them on the ground, the odds of it being ordered is greater than if I had 20 quarters and threw them on the ground, right? So the probabilities of the ordered and random state are proportional to the number of ways that that state can be achieved. So the probabilities of the ordered and random state are proportional to the number of ways in which that state can be achieved. Boltzmann is our scientist here that came up with an equation relating entropy to the probability. So Boltzmann he said that the entropy of a state is related to the number of ways in which that state can be achieved. So his equation, S for entropy, notice it's just entropy also, not entropy change. And that's equal to K, which is our Boltzmann constant, I'll write that down in a minute, multiplied by the natural log of omega, sometimes W, it should be omega, but I have seen it just as W before. And essentially what this is the number of ways that we can achieve that state. So the number of ways a state can be achieved. K I said was a Boltzmann constant, and then ln, of course, is the natural log. And the Boltzmann constant is actually equal to our gas constant divided by Avogadro's number. So a derived unit for sure, right? And it is equal to 1.38 times 10 to the negative 23rd joules per Kelvin. I generally don't ask a lot of problems with this. I just want you to kind of understand the relationship. So kind of, for example, the extreme end of things, if omega is equal to 1, right, there's only one way that we can achieve a state, then it's going to be perfectly ordered, right? The natural log of 1 is equal to 0. So my entropy is then equal to 0, right? 0 times Boltzmann constant is going to be 0. So it's perfectly ordered, right? Remember, if it's 0, it has no disorder. Entropy is a measure of disorder. So if we say its value is 0, it has no disorder, perfectly ordered. Right? If I had 1/4 and I was going to throw it in the ground, and ordered is either landing heads up or heads down, it's going to land one of those ways, right? It's going to be perfectly ordered. As the number of ways that we can achieve that state, right, my value here for omega goes up, my entropy is also going to go up. So probability increases, as the probability decreases, my entropy is going to go up. It's related to the odds that it can do that. Right? If I was to, let's do an atom. So let's say we have an atom. Let's do a crystal. Sorry, guys. I'm changing my mind here. So let's say we have, what is the entropy? Of a crystal. So just a solid, right? Remember there was crystalline and amorphous solids. When I say a crystal, I'm talking about an ordered solid with 20 atoms. And then let's just say there's 2 different states, so 2 orientations. So since I have 2 orientations and I have 20 atoms, the number of ways that I can achieve a state, or the number of states, sorry, is 2 to the 20th. Right? You would take however many ways you have and you would raise it to that power. So like quarters again, there's 2 of them, right? Heads up, heads down. If I had 2 quarters, 2 to the 2nd power. If I had 30 quarters, 2 to the 30th power. If I had a dice, right? Dice has 6 sides, so it would be 6. And then let's say I had 2 die, 6 raised to the 2nd power would be my formula for calculating that. So this is the disordered state. Can be achieved this many ways. And if you, that's actually going to be my value for omega then. Sorry if I'm not being very clear. So if you were to plug that in, take the natural log of it, and then multiply it by the Boltzmann constant, you would get your entropy. I'm not so interested in the calculation. I just want you to see that as you increase the number of ways that you can achieve the state, you're increasing your entropy. So I do want to throw temperature into the mix, so entropy and temperature. We did say in the last video that as temperature increases, entropy also generally increases. So entropy is associated with particle motion. Just in general, particle motion, right? When we were talking about the more bonds we had an increase of entropy because there was more bonding, stretching, that sort of thing. We said there was more microstates. So the more microstates you have, again, you're increasing the number of ways that you can achieve a state. All of this can go back to our Boltzmann equation. So anyway, entropy is associated with particle motion. Random motion increases as the temperature increases. So random particle motion increases as the temperature increases. Right? Remember, the average temperature is the average kinetic energy of our substance. So it increases with the average kinetic energy. Of the substance. So as the energy increases, it actually needs to be distributed amongst my particles, and it can be distributed amongst the particles in a number of different ways, The more ways that it can be distributed, that's going to increase my value for omega again, which then increases my randomness and thus my entropy. So this total energy can be distributed among the individual particles in a number of ways, right? According to Boltzmann, the more ways that it can be distributed, right, that's going to be my value. The greater the randomness, so greater entropy.